Okay, so let me start. So let me thank to organizers for to give me to give this chance to present this work over here. So this work actually is done in collaboration with my colleague Sajal Ghosh, who is an experimentalist. He is interested in tuning the, I mean, uh, he is working in soft matter and is interested in tuning the uh, this I mean the properties of bilayer, and so let me start with this. So basically they are dealing with this material which are, I mean, this surfactant which are having this head and this chain, which is one part is hydrophilic and one part is hydrophobic. And when you put it in water, so they collapse such that they hide the tails from water and expose the water loving part in such that to minimize the free energy. And then you have this with the concentration, various type of self assemblies appear depending on the situation. And this, I mean, in some cases, these type of, they form this cylinders which actually form this hexagonal phase, and in some cases they actually form these type of symmetric phase, which is this bilayers or lamellar phase. I will be more interested in these two type of phases. So what you can see over here, they can form various different phases, and interest, I mean, will be like there are this type of phase is also there where you are having inverse hexagonal in which the heads are which is containing the water inside and the tails are exposed outside, and this is inverse micelle. So this type of phases, I will be more talking about this type of phases further. So let me directly come to the material what they were working with. So they were using this something called sodium disulfide, which has this carbon chain and this head. So when you mix with water, this sodium ion will go, and then you are having this negative head and this chain, and its phase diagram long back in 1988 people have published this. This is the self assembly they form. So they are working at 30 degrees centigrade. If you come across this and you are go for this 40 weight percent, then so they will be forming this hexagonal phase, which I showed you earlier, which is a long cylinders, and then so this is particularly the point where they are working. And here what they want, so they want to mix this thing, I mean they want to tune the head-head interaction which is over there, and such that, so they wanted to see how this affect the self-assembly. So, so in this pure case, you are having this two heads which is negative and this tail, and you mix with this another positive head, so they are calling this ionic liquid. They are mixing it, a very small concentration of this they are just going to mix in it. And so this is the original sodium disulfide, and they are mixing over it. So tail is less, but head is having the positive charge, this is having the negative charge. And so this is the way they were setting this experiment. So this is the total surfactant. So this is the ratio of total surfactant divided by this weight, so weight percent. So they fix this, and they are playing with this SDS and BMIM. So this is the SDS and this is BMIM. So this is the ratio they were changing. And then what happened? So this is the I mean X-ray diffraction they have got. So when you are over here with the pure SDS case, and in this pure SDS case you are having this peak particular which correspond to hexagonal phase, which is HI. So they have calculated what is the lattice parameter associated with that, and they are mixing very small amount of ionic liquid BMIM in this case. So by increasing this, what happened, you are having this mixture of hexagonal and lamellar, and then when you increase further a very small amount, you can see they have gone only 0.1 ratio of this, then they disappear, which is a indication of lamellar phase. So they are symmetric kind of phase. So let me just if you recall, so this was the hexagonal, and this is the lamellar phase. So now they are having this. They increase it, and then it goes back to this one. So here they asked me this question that the experimental result was this, like you are having alpha, which is the ratio of mixing. So you are having in this situation, this is the lattice parameter of hexagonal phase, then you come here. So these are the spacing between these stacks or lamellar phase, and this lamellar phase stays up to here, and then it suddenly goes back to this hexagonal phase. So they were working at, this was the temperature. Now the question was what is happening over here, and they were asking, I mean, the idea was like when you are having this phase and you are mixing something with it, which is so what is happening, so it is having negative heads, a pure state you are mixing with something which is having a positive head. So this head-head interaction effectively what is changing the size of this head, and then this curvature is reduced and you are having this flat layer and you are going back to this situation. But then with this concentration, then question was what will happen. I mean, suddenly it goes back to hexagonal phase. So they have done some other things as well, like this rheology. So I am not paying attention, but only the result I am showing what they have got. So this is the first hexagonal phase they were getting. We are denoting with H1. And then lamellar phase, hexagonal again, they are denoting by H2. So this is the question. This structure was more rigid, and question was whether it is an inverted micelle or not. This was the question they were asking. So what I did, I asked this to calculate to this packing parameter. And this packing parameter, you can see that, or the shape parameter, you can see that if you are having this type of molecule, so we are comparing with the original volume of molecule with a cylinder. So if you are having this A naught and you having this extension length L, so this is A naught by L. So if you are having A naught, so cylinder and volume, so if volume is less than the cylinder, so for example, if it has a cone shape, so then in this cone shape, you know that this will be having 1/3. This ratio of cone and the cylinder is 1/3 of the same base. So if you are having this ratio is less than 1/3, so this individual thing will be behaving like a cone, and the aggregate will give you the spherical shape, and when you this changes, this ratio changes, so you are having the cylindrical micelle, and if you are having this ratio is almost 1, so individual shape will be a cylinder and the aggregate will form a plane bilayer. So if it is a inverted truncated, then you are having this will be less and volume will be more, so then this will be greater than 1. So this will be inverted micelle, and so they want without any sophisticated experiment they want to do this. So I suggested calculation of this average density. With these things I was able to manipulate what was the I mean these packing patterns. For example, if I assume this is the shape, these were the two. This is the question. So assuming these two shape, so and with the average density we calculated, basically I was able to calculate. So you see that if I assume this, I can this ratio of this volume and this distance which they are measuring in experiment, utilizing this I was able to calculate how much volume is associated with it and how much area is associated with this per head. And then assuming this both, if you are having a zero mixing and so zero mixing, this was a direct micelle, that is not a problem. We tested it with that and we find this is the calculated value, and you are having the theoretically this was the theoretical value. So it was safe. So it was cylinder. We just testified. And for the case when they mix this thing, you are having two choices, either the reverse micelle or direct micelle. Both the cases we tested. Calculated value, assuming this phase was giving this, but actually it should be greater than 1, so this is not there. So you are having going back to direct micelle. So it's not inverted, but it's a direct micelle. So this was verified. Now, so you are having this thing which is having, you mix it and you ionic liquid, you are having this and you are going back to direct micelle. So the explanation which I can think of is that, so this head-end interaction is actually overcome by this tail length, which was a short tail length, the effect of this, because this they will apply the pressure over there, so that will be balanced with that. So with this input, they have done another experiment, and with this experiment they were using this some other molecule which is having tail length less than this, and with that they did some experiment, and similarly with another molecule which was having a big tail length, they did this experiment, and with this, so we are having this situation for the short thing. They were having only this did not appear, and it goes back to cylindrical, but it's having a this thing. Okay, so and then for the long they are having this thing. So so this thing is verified. After that, we wanted to do this test with setting up the simulation. I started with dissipative particle dynamics simulation with my student, and we have some success of it. And if you have you interested somebody, I can show you those things. Okay, thanks.
Thank you, Speaker.